Welcome to StarQUIC, tuning congestion control algorithms for QUIC over low Earth orbit satellite networks. My name is Victor Kamel, and this research was done with Jinwei Zhao, Daoping Li, and Jianping at the University of Victoria. We know that Starlink hands over on a fixed 15-second interval on the 12th, 27th, 42nd, and 57th second of every minute. This causes latency spikes and packet loss that degrade transport layer protocol performance. On the left, we have a latency trace from a Starlink user terminal located in Victoria, BC, with the handovers plotted with vertical purple dashed lines. This user terminal does not use intersatellite links. And on the right, we have a latency trace from a dish in the Seychelles. This one does use intersatellite links. We can see that just after handover, in both cases, we see spikes in the latency. And in addition, we see that in every 15-second interval, the baseline latency changes. It might go up, down, or remain the same. In addition, we see that, especially in the case of the dish with intersatellite links, packet loss, which in this case is packet loss reported by IRTT, aggregated at 1-second intervals, seems to be correlated with the handovers. So in this work, we're looking at congestion control algorithms, as we have noticed that current congestion control algorithms for QUIC do not perform well for transmission over low Earth orbit satellite networks such as Starlink. In this work, we looked primarily at two categories of congestion control algorithms: loss-based and delay-based. Loss-based algorithms such as TCP-Tahoe, Reno, and QUIC rely on packet loss events as the primary signal for congestion, and may mistake packet loss during handover as indicators of congestion, resulting in instability. Delay-based algorithms, such as BBR version 1, which estimates the bandwidth delay product, is sensitive to variations in delay and changes in round-trip time, which change during and after handover. In practice, some loss sensitivity is useful, so later revisions, such as BBR version 2 and version 3, are somewhat loss sensitive in order to compete more fairly with other algorithms. So here we want to use the predictable aspects of handover to mitigate the impact of the unpredictable aspects. Specifically, for loss sensitive algorithms, we propose a congestion window freeze mechanism, which will prevent losses incurred during handover from being interpreted as congestion. However, sometimes packet loss is not recognized immediately during handover. For example, in the figure on the right, we see that packet 1 is lost during handover, but we only learn of this after we have received acknowledgement for packet 2. This could be even worse, for example, in the case of QUIC's delayed acknowledgements, which might even take longer for us to learn of this. Therefore, in our approach, we keep track of when packets are sent, and only decrease the congestion window if they are sent during handover. In order to create our evaluation, we used PicoQuic as our reference implementation, as it includes or implements QUIC, BBR version 1, BBR version 3, and other congestion control algorithms. So we set up an emulation based on Mininet, which updates the latency and throughput of the connection based on IRTT and IPER3 traces every 100 milliseconds. In addition, it synchronizes with wall time to hand over at the correct intervals. We also do a preliminary evaluation on real Starlink with dishes located in Canada and in Japan. First, we have to find an optimal congestion window freeze time. We do this in BBR version 3. In this experiment, we're transferring a large file from a server running our modified congestion control algorithm to a client. And we can see that of all of the congestion window freeze times tested, we see that plus or minus 100 milliseconds seems to give the best transfer time, as well as the smallest variance in transfer time. This seems reasonable, as handover typically lasts about 100 milliseconds, and we also have to account for time it takes for the packet to actually arrive at the user terminal. Next, we look at our emulation both for BBR version 3 and QUIC, with our congestion window freeze set to plus or minus 100 milliseconds. For BBR version 3, we see that compared to the non-modified algorithm, our algorithm of modifications of the congestion window freeze improves both the transfer time and the variance. In fact, it is almost competitive with BBR version 1, which is not loss sensitive at all. On the right, we can see, based on the CDF, that the throughput is consistently higher with our approach. We see that QUIC doesn't perform quite as well. This is because the version of QUIC implemented in QUIC is non-standard and has a congestion window recovery mechanism, so that delayed packets that eventually arrive don't decrease the congestion window. Since our emulation only varies the throughput and latency, but not the packet loss, we see that it accomplishes similar effect to our congestion window freeze, but we expect that in a real scenario with packet loss, our approach will have some benefits. Next, we look at transfer times for BBR version 3 and QUIC over real Starlink, with the congestion window freeze set to plus or minus 100 milliseconds. For BBR version 3, we see that in both the North American dish and the dish located in Japan, the transfer time has decreased and the variance has decreased as well. Next, for QUIC, we see that at least in the North American dish, we also see an improvement. In this work, we have presented strategies that work with loss-sensitive algorithms primarily. However, strategies for loss-insensitive algorithms are important as well. We need to somehow mitigate delay variation during and after handover. One possible approach to this would be to remeasure the delay after handover to have a better updated view of the current round trip time and latency. In addition, we want to try our approach with other constellations, for example, OneWeb. All constellations experience handover, but the characteristics of this handover vary between constellations. I'd like to acknowledge that this work would not have been possible without other Starlink users such as Sean and Dominique, who generously allowed us access to their dishes remotely, as well as our other funding sources. Thank you very much for listening.